All right, BC Calc, we are on day 7 notes here in your packet, and we're talking more about some derivative rules and properties today. So as a quick recap from yesterday, we had at the top of our page the limit definition of a derivative. I know that yesterday we said pretty commonly we'll see that delta x is replaced by an h. So we'll see that very commonly when we're using the definition of derivative. But what we're going to talk about right now, and this might be something you learned in pre-calc honors last year, is an alternate definition for the derivative at a specific x value c. So you can see my diagram here. I have this curve y equals f of x. I've defined, if I want to find the slope of the tangent at x equals c, that would have the coordinate c comma f of c. And to get started, just like in yesterday's definition, we also need another point on the graph. We need to establish the secant line so we can start collecting our ideas about how to get the slope of the tangent line. So this coordinate point I've defined as some value x comma f of x. And therefore, the slope of the secant line would be change in y over change in x there. So for my secant, we have that f of x minus f of c over x minus c would be the slope of that secant line. So then how are we going to make this the slope of the tangent line? If you think back to yesterday's notes, we were looking at that the difference here as being delta x, and we wanted delta x to approach 0. So it's going to be kind of a similar concept. I want to slide this point to the left so that we're kind of approaching c there. So in this case, the way I'm going to express this is it's the limit as x approaches c. That as x approaches c, if we evaluate that limit, that would give you the slope of the tangent line at x equals c. So there's an alternate definition. And again, this is really just for finding a derivative at a specific value of x, like x equals c. And there are definitely advantages to using this limit definition. In fact, we are going to use it to prove something in the bottom half of our notes. So if we're good with that, the bottom half, it says there's a theorem that if we have a function y equals f of x, and it has a derivative f prime of c at some x value equal to c, then we know that f of x is continuous at x equals c. So based on what we now know about continuous functions, we know, and what we're going to need to show, is that the limit as x approaches c for f of x is equal to f of c. That's definitely the condition that has to hold true in order for a function to be continuous at x equals c. And we want to somehow incorporate this idea that we have a derivative that exists at c. And then use that information to say, okay, if the derivative exists, then we're continuous at that value. So there's going to be some, I would say, slightly unique algebraic tricks that we'll do here to make this happen. But first and foremost, I'm going to subtract f of c to this side with the limit. So we get limit as x approaches c of f of x minus f of c is now equal to 0. And what I'm trying to really build towards here is getting that limit definition that we just had up here a moment ago. The limit as x approaches c of f of x minus f of c, all divided by x minus c. So how am I going to accomplish that? Well, if I put x minus c in the denominator here, now I see that limit definition that we wrote up above. You also then have to multiply by x minus c. And I guess the question becomes, like, does that equal 0? So here's what we know. If I were to take the limit as x approaches c for what I have on this side of the equation, remember, the limit of a product of the functions is equal to the product of the limits. So therefore, I can separate it into these kind of two cases and say, what's the limit as x approaches c for this? Well, isn't that the definition of f prime of c? Right? That would be the derivative at c. What's the limit as x approaches c for x minus c? That's going to be c minus c, which is 0. So I get the derivative at c times 0, which of course has to be 0, and we're pretty pleased with that. So that's a quick little proof here using that alternate definition to show that if a function has a derivative, f prime of c at x equals c, then we must be continuous there. So my question for you before we turn to the next page is the converse true? Now, for those of you that had me in geometry a few years ago, although the converse is not a part of geometry course anymore, formal logic statements are really important in mathematical definitions. So the converse essentially means just switching it around. If I switch the order of this if then, if it's continuous, then it has a derivative, is that going to be true? So I want you to think about whether or not you think that's a true or false statement. And of course, if we don't think it's true, then that must mean that you have a counterexample for me, something that would disprove it. If we think it's true, then we might have to develop a proof that proves it's true for all values of x equaling c. So let's take a look on the next page here. And as you can see, as soon as you turn the page, well, it's probably not true for the converse because we have a counterexample. Here's my counterexample that I came up with, y equals absolute value of x. Where might this function be continuous, but not necessarily have a derivative? Probably know already. I think you talk about this in pre-calc honors. Well, it's definitely continuous at x equals 0, right? I can draw my graph without picking up my pencil. The limit as x approaches 0 is equal to f of 0, so we're all good as far as that goes. But does f prime of 0 exist? Does the slope of the tangent line exist at x equals 0? And my really fancy little, I knew this was going to be a problem for me, guys. It's going to take me forever to get this little post-it up. There I go. Oh, it just says no. All that just for it to say no. How silly. All right, so no, f prime of 0 does not exist. Think about drawing the slope of the tangent line at 0. Where would you draw it? Would you draw it horizontally? Would you draw it with a negative slope? You could do that and be tangent at 0. You can even draw lines with positive slopes. Okay, so because of that really sharp corner that we turn for absolute value functions, the derivative will not exist at the vertex of that absolute value. And here's kind of a quick algebraic proof. If I were to find f prime of 0, it would be the limit as h approaches 0 for absolute value of 0 plus h minus the absolute value of 0 all over h. Okay, so we're subbing in that value for x already. And we get kind of a split case here, don't we? It's going to turn into the absolute value of h over h. So on one hand, if we approach 0 from the right, what happens is you can drop the absolute value and let that equal positive h. H over h is 1. But if we approach 0 from the left and we're plugging in negative values for h, when I drop the absolute value, you'd have to negate that expression. This would be negative h over h, thus why I wrote negative 1. So approaching 0 from the right and left-hand sides are not returning the same value, and therefore, since this limit does not exist, we would say that this function does not have a derivative at x equals 0. So the converse is not true. Going back to that statement from earlier, just because it's continuous does not imply that it has a derivative. And by the way, that term means that you hear for having a derivative would be differentiable. So if it's continuous, it does not imply that it's differentiable at that value. So let's go ahead and then take a look at the bottom half of the page here at the, hold on. On the bottom half of the page, I want us to show that the function below has no derivative at x equals 0. So in order to do that, if the function doesn't have a derivative there, we really just want to show that when I approach 0 from the left using our limit definition and approach 0 from the right, that we're not getting close to the same value. So it's going to be maybe just a little bit different notationally because we're not going to actually find the derivative. But if we make a sketch, we can figure out what the slopes of those tangent lines are. So we have this piecewise function. Here's what it's going to look like. X squared when x is less than or equal to 0. It's going to be this left-hand side of the parabola. And then 2x when x is greater than 0. We'll actually find that this is continuous at x equals 0 because 2 times 0 is 0. But then we pick up with a line that has a slope of 2. So again, as you approach 0 from the left and the right, although we're continuous there, the slope of the tangent line is not getting close to the same value, right? These slopes are getting closer and closer to something, but it's not matching the slope from the right side. Let's talk about what those slopes are. So notationally, what you would write here is the limit as h approaches 0 from the right. We'll start with that. Of f of x plus h minus f of x all over h. Well, what's the slope of the tangent line as I approach from the right? It's going to equal the slope of this line. And we'll actually prove that in a moment here. But that's going to equal positive 2. And the way you can actually define that notationally then is saying that this is the derivative of x from the right-hand side. Okay. So on the other hand, if I approach 0 from the left, we would get f of x plus h minus f of x over h. What's going on as I approach this value at x equals 0 from the left? Well, those slopes are getting steadily, they're decreasing, right, in their rate of negativity. As we get closer to that vertex of the parabola, we're getting closer and closer to 0. So this therefore proves that the function won't have a derivative there. Okay, we have this little sharp point that we're reaching, and whenever a graph exhibits sharp points, if it's continuous there, it doesn't necessarily mean it's differentiable there. All right. Okay. Moving on to the next page, as promised, let's actually talk about derivatives of linear functions. So given f of x equals mx plus b, right, y equals mx plus b, that slope-intercept form, we're going to go ahead and find f prime of x. So if I use the limit definition, we'll take the limit as h goes to 0 of f of x plus h. And what would that look like in this example? F of x plus h would be m times x plus h plus b minus f of x, so minus the quantity mx plus b all over h. So what we're going to do is we're just going to clean up the numerator, see what kind of cancels out. So distribute the m to get mx plus mh plus b. Distribute the negative here to get negative mx minus b all over h. And you'll notice the mx's cancel, the b's cancel, and we're left with the limit as h goes to 0 of mh over h. Don't plug in 0 yet for h, right? Definitely cancel those h's top to bottom. Well, the limit as h goes to 0 of m is m. That's it. So what have we just proven here? That the derivative at any value of x for a linear function is equal to m, the slope of the line, which we saw pretty, I think, nicely graphically in the last piecewise that we looked at. Okay, so that's going to help us to develop other derivative rules that we get into in the next few days. But yeah, derivative of a linear function is equal to the slope of that line. I mean, think about it. If you pick any point on a linear function and find the tangent line at that point, it's going to have to equal the slope of the line. Here's the proof. Okay, let's talk about how do we use the calculator to find derivatives. So on the home screen of your calculator, there's a couple of unique things that we can use. And specifically to find numerical derivatives, we're going to use Math 8. And Math 8 is n-derive. Okay, n-derive stands for numerical derivative. Here's what that input screen is going to look like, and I'll show you this on my screen in a moment. Most of you, I'm sure, have an updated enough operating system that it will look like this. If not, let me know. And there's a series of commas and things that you'll have to enter to get the same results. Okay. So if we take a look at this example, what we're going to have to put down here is we're taking the derivative with respect to x. And what's going to get inputted here is the function that we're trying to find the derivative at. What's going to go in this location down here is x equals some numerical value. So if I want to find the slope of the tangent at x equals 2, we would put x equals 2 in that bottom section. Okay. If we're looking at this on a graph, and we'll show you this in both ways in a second. So that's on the home screen. On the graph, when a function is entered in y1, we can actually do second trace, and we'll choose option 6, which is dy dx. the derivative at that specific value of x. So it says use your calculator to find f prime of 2 given the function f of x equals x squared. Okay. So let's see if we can do this in both ways. If we on the calculator hit math and then choose option 8 down here and derive, we want to take the derivative with respect to x for the function x squared. And it already has entered x equals for me there. So we're going to do x equals 2. Is that what I said? Yep, f prime of 2. And the slope of the tangent line at x equals 2 is 4. How nice is that? All right, so f prime of 2 is 4 from the home screen. If I did n derive ddx of x squared at x equals 2, we find that f prime of 2 is 4. All right, the other way that I said to do it is if we go to y equals for a second and we type in y equals x squared as our function, and we go to the graph, we can do second trace, calculate option 6, dy dx. And so it says calculate derivative at point at x equals 2. So we'll type in 2, hit enter, and it gives me that slope dy dx would be 4 there. Okay. So it actually gives me the coordinate of that point as well, which is nice. And then the slope of the tangent line is listed above it. So if you have any questions about how to use the calculator to calculate some derivatives, you'll let me know. All right. Let's go on to the next page. All right, on the next page, if we take a look at just finding some more derivatives, I think I'll let you try 1 and 2. So we'll talk about those tomorrow in class, but see if you can use your calculator to find the derivative of sine x at x equals pi over 4. Right, so try it using n derive, or try it using typing it into y1 and using dy dx from there. Try that for number 2 as well. Here's another example I'll kind of let you take a look at. Write the equation of the tangent line at x equals -1. Boy, that doesn't look like something we can find the derivative of pretty easily. So it's a good thing we can find that numerical derivative at -1. Carefully type that in. It also asks you for the equation of the tangent line, so make sure you include that once you find the slope at -1. All right, so then finally from there, number 4, this one I'll do with you just to make sure we understand how to graph a derivative and the function on the same set of axes. Okay, so I'm actually going to type this into y1, and then I'll show you what the entry looks like for y2 to graph a derivative of a function entered into y1. Okay, so if we go to y1 on the calc, we've got x to the 3rd minus 4x minus 5 is going into y1 right now. And then in y2, I'm going to do n derive here. So we're going to go to math 8. What am I doing n derive for? Well, I'm finding the derivative with respect to x. I want to do it for what I have in y1. So to get y1, there's a few different ways to do that. You can go to vars. Slide this up a little bit. So if you go to vars right here next to clear, you can go over to yvars, hit enter for function, and then enter for y1. That's a way to do it. There are some shortcuts, and to be honest, I don't remember if it's like alpha trace or alpha graph. Maybe it's alpha trace. There it is. Yeah. Alpha trace gets you y1 right away too, which is kind of nice. Okay. So however you enter y1, that's up to you. But then what am I going to set x equal to? Let's set x equal to x. We wanted to sketch the derivative for every value of x, not a specific one. And if I zoom 6 from there, we're going to get a cubic polynomial graphed. Maybe. It's really thinking hard about this. I actually have mine graphed on simultaneous mode right now. So if you go into the mode, you can switch it to simultaneous or sequential. It's up to you. But mine was thinking real hard because it was graphing both at the same time. So we've got our cubic polynomial, and then the right graph is the sketch of the derivative, which is pretty awesome. All right. So another interesting way to use the calculator to kind of take a look at some derivatives here. I'll let you sketch that here. But the last part of today's notes is going to be about something called the symmetric difference quotient. So how is the calculator doing this? How does the calculator determine the values for discrete derivatives at x equals 2, at x equals 0, and so on? It uses something called the symmetric difference quotient, and you will see this come up in textbook homework. So what does the symmetric difference quotient do? Here's a diagram of what we have according to that slope. Essentially, if you want to find the derivative at some point a comma f of a, what the symmetric difference quotient does is it goes kind of equally spaced. It goes h units in each direction from the point that you're trying to find the derivative at. And then it calculates the x values and y values at those locations. And it gets really, really close. And essentially is finding the slope of a secant to approximate the slope of the tangent line at that value. So a couple quick notes about symmetric difference quotient. The calculator will use this process and go h away on either side of a, the value that we're trying to find the derivative at. Now, if you've already tried number 2 from the last page, you'll see this is why this gives us 0. But we know that this isn't true. So we're going to talk about this in class next time I see you, but we know that absolute value of x is not differentiable at x equals 0. But the calculator tells us this, which is a little bit of an issue, isn't it? Why is it telling us that the slope is 0 there? Because it's using the symmetric difference quotient to evaluate it. All right, so it's coming up with the slope at that point. So we have to be a little bit cautious about just always relying on n-derive on the calculator. But we'll kind of reference this a little bit more in class tomorrow. Otherwise, that's it for today's notes. Let me know if you have any other questions.